Hello everyone. Today we will look into the next method, which is the extension of the minimum potential energy method called as Rayleigh Ritz method, or also called as RR method. Rayleigh Ritz method, which is also called as RR method. Now this Rayleigh Ritz method, there are certain steps that we follow in order to obtain the solution for a given problem. The steps are more like the extension of minimum potential energy. Hence, the very first step that we follow is again to obtain the potential energy functional for the given body or the given problem, for the given body or continuum or the present problem. The second step, once we have formulated the potential energy function, the second step is we need to assume a trial displacement function that satisfies all the boundary conditions, and also the trial function can be either polynomial or trigonometrical. So the second step will be to consider a trial displacement function satisfying all boundary conditions and this trial function, the trial function that we consider can be either polynomial or trigonometrical in nature. So once you have assumed a proper trial function, the third step will be to substituting the trial function to the minimum potential energy functional. Substitute the considered trial function, which can be either trigonometric or polynomial, to the potential energy functional. Potential energy functional is strain energy plus work potential. To that you will be substituting the trial function that is assumed. Once it is substituted, the potential energy functional is minimized. Fourth step is to minimize the potential energy functional. This will be minimized in terms of the Ritz coefficients that will be part of the assumed trial function, with that can be either polynomial or trigonometric. So once the function is minimized, potential energy functional is minimized, and the unknowns are obtained, we can obtain the displacement from it. The fifth step is to determine the unknown displacements, and from that the stresses and strains, and further the unknown stresses and strain. So in order to obtain or understand these following steps in a very better way, let us try to solve one problem. Let's begin with the numerical. So the first numerical goes like this: by Rayleigh Ritz method, for a bar of cross-sectional area, for a bar of cross-sectional area capital A, elastic modulus capital E, subjected to uniaxial loading, P. Show that at a distance x, from fixed end displacement is u equals p by ae into x. So this is the displacement at the fixed end that we need to prove, and hence determine the end deflection and the stress to which the bar is subjected to. There is a small diagram that we have for this. The bar is of uniform cross-sectional area. And the load that is being applied is axial one end is fixed, cross-sectional area A, Young's modulus E, the length is capital L. The load that is being applied is P. Now, going by the steps that we had talked of, solution, we need to first obtain the potential energy function for the given body. So, potential energy functional is potential energy functional pi equals strain energy plus work potential. So, for bars, strain energy is equal to AE by 2 limits from 0 to the length of the bar, dou U by dou X whole square into dx. And work potential is, since it is a point load, minus P into the displacement produced, U1. Now, substituting these into the potential energy functional, therefore pi will become, pi will be equal to strain energy is AE by 2, 0 to L, dou U by dou X whole square dx minus P into U1. Let's say this is equation 1. Okay. Now, let the approximate or the displacement for trial displacement function be, let the approximate displacement function be, say U equals A0 plus A1 x. All this as equation 2. We have assumed a polynomial displacement function for this. So, applying the boundary condition to this, applying the boundary condition at x equals 0, U equals 0. Therefore, this equation 2, when U is 0 and x is 0, A0 will be equal to 0. This is the first value of the coefficient. So, equation 2 will become U equals A0 is 0, so A1 into x. So, let me call this as equation 3. Now, the second boundary condition is at x equals L, that is capital L, length of the bar. At x equals L, U is equals to U1, hence equation 3 will become U1 equals A1 into L. I will call this as equation 4. Now, U1 is obtained. If you observe, the trial function that we are taken when we want to substitute something into the potential energy functional, we need to find out u1 and dou u by dou x. So we differentiating equation 3 which contains u, equation 3 with respect to x, dou u by dou x will be equal to a1. Let me call this as equation 5. So substituting the values of u1 and dou u by dou x in equation 1, we get pi equals, it was a by 2 integral 0 to L dou u by dou x whole square it was. Now it will be a1 square dx minus p into u1 it was. So u1 when you substitute it is a1 L. Now when you integrate this, pi equals a by 2 a1 square x from limit 0 to L minus p a1 L. When you substitute the limits, pi is equal to a by 2 a1 square L minus p a1 L. Now this is the final potential energy functional. Now we want to minimize this potential energy function. So minimizing the above function, minimizing the above functional dou pi by dou a1, because a1 is the variable here, p, l, a, e by 2, all these things are constants, which values are known. Dou pi by dou a1 is equal to a by 2 2a1 L minus p into L, or it will be ae L a1. Whenever you minimize something, it should be equal to 0. So dou pi by dou a1 will be equal to 0. This will mean that minus pl equals 0, or a1 is equal to pl by ael, or a1 equals p by ae. Now substituting a1 in equation 3. Substituting a1 in equation 3, which is this equation, you'll get u equals p by a into x, which is our required deduction from the problem statement. So once we have this, we'll calculate strain is nothing but epsilon, which is change in small length over the length that we have considered, dou u by dou x. So dou u by dou x is nothing but a1 from equation 5, which is equal to p by ae. Stress is equal to sigma, which is equal to Young's modulus into strain epsilon, which is nothing but E into epsilon is A1, which is P by AE, P by A, the formula which we are familiar with. So this completes the solution for the first numerical. We'll continue with further numericals in the upcoming sessions. Thank you.